Okay, we'll start recording. And let me share a whiteboard here. Oh, where's share? Share whiteboard. By the way, I have no idea. Is this a good format? Do you guys like this? Or how does this compare to like what your other professors are doing? I don't know what the other professors are doing. So I have no idea if I'm doing a good job of dealing with this pandemic thing or like a horrible job, or, I mean, obviously you're the ones that are showing up, so you probably don't hate it, or maybe you do, I don't know.
Yeah, I mean, it's helpful to me. I am really bad at keeping up with work on my own. So this kind of forces me into like keeping up with the new material,
Mhm.
which is why it's quite helpful for me. But yeah, the format works just fine.
Okay, cool. All right. I mean, I assume the other professors were doing something along these lines, but I don't really know. So anyway, I'm gonna answer a question that Hannah emailed me real quick. So if you have a triangle, oh, love it. Great way to start the morning. Okay, so you have a triangular prism. Okay, I'm gonna try to draw this as best I can. Let's just say it's oriented randomly, which is probably not a good way to have this thing oriented, but whatever. Oh, I'm gonna take the whole line. Okay. Okay, so you have a triangular prism and you're looking for the centroid. So the key usually, well, okay, this is a bad drawing, but so usually what's going to happen is, it depends on the way the axes are oriented, but let's suppose we've got one axis going this way. Okay, with respect to that axis, the centroid is going to be like right here, right? So there's like an axis like right along here. Okay, and the reason for that is because with respect to this axis, this thing is completely symmetric. So if I were to slice it along that line, half would be over here and half would be over here, and they'd be exactly identical. Right? So if it's exactly identical, it's the same thing as like a rectangle. Like when you're looking at a rectangle, the centroid's right here, because if you were to slice it along this line, okay, there's half up here and there's half down here. And if you slice it along this line, well, there's half here, and they're exactly identical. So it makes it kind of quote unquote easy. So with the triangle, with the 3D triangle, whatever axis this is, let's say this is the x-axis, okay, then you're just going to go right in the middle in that direction, because if you slice it along here, it's going to be right in the middle. And that's not where the centroid is, right? It's actually going to be somewhere in here, but it's going to be on this plane right here that I've just drawn. Okay, like, I mean, I can't really draw that, right? Now, with respect to the other axes, so like if we've got this triangle and it's like this, okay, and this is like y, and this is z, okay, well then it's 1/3 of the way from this flat edge, 1/3 between here and here, so it'll be like here. Okay, let's just draw a line there. And notice this one's it's not symmetric, so it's not going to be halfway between this line and this point. Okay, so that's when we need to look it up on the chart. So this becomes h over 3 and 2h over 3. So h over 3 and 2/3, if this is h. I guess that's technically b, right? That's the base. Okay, and then for this direction, okay, it's the same. So this is going to be, this is h for the whole thing. This is h over 3, and this is 2h over 3. Right, and so then I guess what I was trying to draw over here is if this thing has some dimension going x into this direction. So let's see, we've got h over 3 or b over 3, so we're like right here. But then if we're going to go into this dimension, it's going to have to go over here halfway. So like right there, maybe, if I could draw that. Does that make sense? Is that at all helpful, or?
Would you just be dividing that part by 2?
Yeah, so we would divide this side by 2. Yeah.
Okay, so it'd be like h over 3 divided by 2 or something like that.
Well, no, so the x coordinate would be, so I guess x comma y comma z would be, I guess if this is the origin, right? So x is measured well, X should be measured this way to make it to keep it right-handed. So then X should be, I guess, but we need a thickness. What do we want to call that? I don't know, we'll call it L. So it would be negative L on 2 for the X. In the Y direction, it would be B on 3. And the Z direction would be H on 3. In this particular, case. Does that make sense?
Yes.
And that negative sign just comes about because I wanted to have a right-handed coordinate system. So, okay, so yeah, so that goes really for any prismatic solid. So if I give you any solid, so if I give you like a, I give you a, something like this, you're like, okay, well, where's the centroid? Right? And you're like, okay, well, we've got a circle. I look up a circle. The centroid of the circle is right in the center of the circle. Right? Okay, great. And then you're like, all right, well, but where is it like in this direction? Right? Well, if I slice it right through the middle, it's the top and the bottom are exactly the same. So it's going to be right there. Or if I gave you, a rectangular solid. So if this was a rectangular solid, same deal. It's like, well, how far in do I go? Well, if I slice it along this line, it's the same on this side as it is on this side. So it's going to go right in the middle. So it's like right there, halfway back, even with this line. I mean, obviously I can't draw that very well, but I don't know, something like that. Or, any prismatic solid. A prismatic solid is where it's got a base on the bottom and a base on the top, and they both have the same area, and it's all the same all the way through. Okay, so it could just be something random. Okay, and if it was the same thing on the top, I mean, obviously I'm not doing a great job drawing that, but so this would have to go to there, this would have to go to there, this part right here, go to, whatever. Okay, any kind of random prismatic solid. Okay, now I don't know where it is in this shape. That, based on how I've drawn it, you might have to do some calculus to figure that out because it's just some random shape. I'd have to give you an equation or whatever. But in the vertical, it's halfway between here and here. So it's going to be, like right there in the vertical. Okay, so the key is like, is it prismatic? Yes. We've got a base here. And then we've got a base on the backside, which is identical, and all the way through it has the same, what do you call that? The same cross-sectional area. So therefore, you can just put it right in the middle. So hopefully that's helpful. All right. So today, let's see, we're going to do, sorry, any questions? Does that make sense? Okay, I'm not hearing anything. So
I'm good.
Okay, holler if that's no good. Okay, so I want to go to Connect and find a practice. Wait, did I post these yet? No, I may not have posted these practices yet. This could be problematic. I could be behind. I am behind, aren't I? I haven't posted because we've done 2 where we did centroids, right?
2 problem-solving sessions?
Yeah, we have.
Yes.
It's really time to move on to moments of inertia. Let me pull one up off the internerds, and oh, that's great. They start right off with give me one second. Huh. They're really all about the they like the integration right off the bat. Okay, let's do some integration. Okay, how comfortable are you guys with integration?
I mean, I can do it.
Okay.
Not my favorite thing.
Okay, well then let's just keep doing it, and we'll try to make it a little bit more comfortable. Okay, so identify the expression for the moment of inertia of the shaded area with respect to the y-axis that is determined by direct integration. So basically they want you to find, I'll draw this for you first. I think that way we can think about this. I'm just because otherwise I'm just saying a lot of words, right? So here's y, this is x. We've got some, some shape that looks like this. Okay, and y equals k x minus a squared. And this would be, this is a b, this is a. Okay, and so what they want, so this is given and required, they want I, y equals what? Okay, so before we like really get into these problems, yes, I am behind. I'm giving you guys homework. I'll have to extend it, I guess. Okay. So so when we think about IY, so what this means, sorry, let me, what this means when we talk about IY. So the moment of inertia is basically how well it's going to resist bending if you try to bend it around a specific axis. So in this case, this little y right here tells us that we're bending it around this axis right here. Okay, so the equation for the moment of inertia is I equals the integral of, now I like it as r squared dA, like this, just because that's the general form. So basically this r right here, that is the distance between your block. So I guess there's two ways to do it, but yeah, okay. So this r squared right here, this is the distance between your block and the axis. Okay, so in this case, just like when we were doing the other one, I want you to remember that the location here is x comma y. Okay, and that means that this distance right here is x, and this distance right here is y. Okay, and so we're going to draw our little block. Okay, and you can do horizontal or vertical boxes here. I'm just going to guess, and we're going to start with vertical, which is usually the easiest in this case. Not always. And so we're going to just kind of set this up. So in this case, we're doing IY equals integral. Now we need, okay, so let's go over here and let's think about R. Okay, what is the distance of this box from the red line? Okay, so that's my radius essentially. Anyone? Nobody? No volunteers?
No.
Is it something minus a?
Okay, let's see. Okay, so we want to know the distance of this box from this line. So I want to know this distance right here. I just said what that distance was like a few, maybe 60 seconds ago. It's a letter. Okay, so this point right here is x comma y. X means we're x from here, and it means we're y from here. So I want to know how far is it from here to here?
It would be x.
X, right. So this distance here, okay, is x. So r equals x. Okay, now we need dA. Okay, now I need to figure out what that dA is. So the area of a rectangle, so here's my rectangle. Well, there's my rectangle. Okay, and it's got a base, which is going to be, well, let's look at that. It's dx. Okay, and it's got a height. Can we see the height? Somebody else? Okay, so I'm looking for this height right here. What's that?
Y.
Y, right, it's y. Okay, so this is going to be y. Okay, that's the height, and then the width is dx. Okay, so now I can plug these into this formula over here, and I can get r squared, that's going to be x squared. Okay, dA, which is y dx. Okay, so we can go ahead and solve that. Okay, so the problem here, of course, is this dx. Well, it's not really the problem, but the problem is this y. We need everything to be in terms of x's. So instead of y, I'm going to plug in all this stuff right here, and we'll get the integral of x squared times, in place of y, I'm going to put kx minus a squared dx, like that. And then I need the limits of integration because I'm going in the x. So it's going to start at 0 and it's going to go to a. So 0 to a. Okay. And I'll do a couple of these this morning. So if I can find a few more. So IY. So now at this point, this is just straight up calculus. Okay. Like, it's just like, can you remember, the product rules and all the silly rules. I'm going to go ahead and expand this x minus a. I'll do it down here. X minus a squared. What's that? X squared minus 2ax plus a squared, I think. Okay, I'm going to take this k, I'm going to pull it out because I don't want to deal with it. K goes out. Not 0 to a. We're going to go ahead and integrate this thing if we can. No, we're not yet. Okay, a to 0. I'll get x to the 4th minus 2ax cubed plus ax squared dx. Okay, so IY equals k. This is going to be x to the 5th. Maybe we'll just put a bracket out here. 1/5 x to the 5th minus, this becomes x to the 4th. It becomes 1/2 ax to the 4th plus 1/3 ax cubed. All right, and we're going to evaluate that from a to 0. Okay, so IY. I mean, kind of sucks in this case, right? It's not really, not really terribly fun. I feel like there's a problem here. A squared. Oh, this should be a squared x squared. There was a problem. So we've got to the 5th, to the 5th, to the 5th. Okay, we're good for units. Okay, so then we've got k. And obviously the zeros don't really matter. So now I've got 1/5 a to the 5th minus 1/2 a to the 5th plus 1/3 a to the 5th. Okay, so IY becomes, let's see, so 1/5 plus 1/3 minus 1/2. Dang gummit. So I guess, how many 30ths is this? 30ths, 15ths? No, 30ths. Oh man. Let's see. So we got 6 30ths here. We've got 15 30ths here. And we've got 10 30ths here. So that's going to be 16 minus 15. So it's 1/30th. So 1/30th k a to the 5th. Okay. There you go. What a horrible answer, because you get it and you're kind of like, well, I don't really know if I should feel good about that. I never really like moments of inertia, because you get an answer and it's to the 5th power. I mean, it's usually, so the units are to the 4th power. This k probably has units of 1 over, it has units of 1 over length. So your answer, if we had numbers here, would come out as something to the 4th power. If not, you made a mistake. Like millimeters to the 4th or whatever. And there's no way to look at it and go, oh yeah, that totally seems like it should be, 420,000 millimeters to the 4th. And that's a very unfortunate thing when getting these, because you can't look at it and go, oh, like obviously. So, all right. So let's try another. Any questions about this? I'm assuming you have a few, but I'm going to work another one. But if you have something about this one, by all means, let's hear it and let's talk it through. And you know, and then you can keep an eye on that and see if it makes sense on the next one. Okay, incidentally, there is another way to do this. It's less easy in my opinion. You could have done a box going the other way. So you could have done it like this, with the box going this way, if you wanted to. But if you do it that way, let's go ahead and do that problem. Let's see. So the formula is kind of different if you're going that way. So you should notice that if you do it this way, okay, this is just a general box right here. Okay, come on, you can erase. Okay, so this is a general box. And what we're going to do in this case is I want the I and the Y. And what I'm going to do is I'm going to integrate from here to here, from 0 to B. Basically, so what you should notice here as far as R's, if we started thinking about R, well, what is the R in this case? Well, the R for this box is not clear, right? Because the radius here and the radius here and the radius here and the radius here and the radius here, the radius is different everywhere within that box. Okay, I chose a box here where all of these have the same distance from the thing that we're circling it around. So that kind of makes things like, that makes this equation really nice. Okay, in this case, however, we can't do that because like if my box looks like this, the R is not the same everywhere. So what we're going to do is we're going to sum up the moment of inertia for every box. So here we've got a box here, and basically I want to know, I don't really know how to say this, but let's say IY for the little box. Okay, and so we're going to sum up all the IYs for the little boxes. Okay, and we're going to do that from here to B. So that'll be dy in this case. So I'm just going to sum them all up. I'm trying to think if that's anyway. I'm going into uncharted territory. I never solved them this way, so I'm worried about getting this wrong. But so what?
Would you ever have us do this form like on a test?
No, but you could do it. Is kind of what I'm. So if I asked you to solve this problem for IY, you could do it either way. Okay, so I'm just saying, like if you drew the boxes the wrong way, you could still solve it. Okay, and so what you would do is IY for the little box. Well, if you look it up on in your chart, it's going to be 1/12 the base times the height cubed. Okay, so so what we need to do then is let's see. So in this case, the problem here is that the base in this case is this guy right here. So that becomes dy, and the height cubed is this distance, which remember every point along here has a point x comma y. Okay, so this distance right here is x, like that. Okay, and then 1/12. So that's IY of the rectangle, like that. And so we could plug this in right here. And I think we would get IY equals from B to 0 of 1/12 x cubed. Oh, sorry. That's where the dy came from. Sorry. It's going to look like that. Dy like this. Okay, so we're just summing up the moment of inertia of all the rectangles. What's nice is that they're rectangles, so you don't even, like before you leave this course, hopefully this, you know, without even trying this, you will have this memorized, 1/12 base height times height cubed, because it's like really common, it just shows up all over the place. Okay, so if we solve this, we get IY equals the integral from B to 0, well, let's pull that 1/12 out front because we don't want to fiddle with that. But again, we've got a Y here and an X here. So, oh, we see, now this is where this one gets ugly, and maybe we'll stop it here. Because what we would have to do is we'd have to solve this equation right here for for y. So it becomes, I mean, for x, so it'd be y over k square root plus a squared. Oh no, we got rid of the square plus a. Right? So something like that. Let's see, x minus a, square it. Yeah, that's right. So then so then we'd have this cubed, which would be square root of y over k plus a cubed dy. Okay, and probably no one really wants to fiddle with that. Okay. I mean, yeah, that's not going to be fun. I mean, you'd have to expand that third until you had like a really large polynomial. So you could get like y to the 2/3 or y to the whatever, and it would just be totally annoying. So I think probably already you guys are looking at it going, I'm never going to do it that way. Which, but you could, okay? And there's almost certainly times when this would be easier. If you click around the internet, you will see people solve it this way. All right, let me find another one of these. Let's see. Let's see the next one. Oh, okay. Yeah, so this one's going to be a little bit harder. It's similar look. Let me clear all drawings. Okay, identify the moment of inertia of the shaded area with respect to the x-axis by direct integration. And maybe we'll do the y-axis too. I want to kind of just milk this for as much as we can, because I'm hopeful that you guys will start to be able to see when these things are x and when they're y and when they're not, you know. So here we go. So here's the shape. Y equals kx cubed. And this will be b, and this will be a. Okay. So they want to know, so this is given, required, I, y equals blah, 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 question mark. Okay, so this is our axis right here. All right, so before we solve this, somebody want to tell me which way we would prefer to draw our box? Okay, remember this is the formula.
Same way as before from the x-axis up.
Wait, yeah. So we want them to be parallel to the axis we're taking it with respect to.
Yeah.
So ideally, we're going to go like this. So notice that the box is parallel to the line, to the red line. Okay, that's important because that means that every point in that box has the same radius. Okay, that's key. Okay, and what is that radius? Okay, let's remember this point right here is x comma y. So what's that radius? X, okay? Because x tells us how far this point is from the y-axis. Okay, so r equals x. Okay, now I need to figure out this dA right here. Okay, and the width of that box, what's the width of that box?
dx.
Dx, yes. And what's the height of that box?
Y.
Y, right, because y tells us how far this is from here. Perfect, great. Okay. All right, so I hope this one would be a little bit harder. Well, maybe, maybe when we go and do the other side, it'll be harder. Yeah, it'll definitely be harder. That's okay, because you guys are seeing it. So that's the key here. So we'll say IY, so that's with respect to the y-axis, equals, let's see here, r squared, so it's x squared. Okay, it's best when you do these things if you have sound effects. At least I find that. So 0 to a, and then dA is going to be y dx. Okay, so then let's see here. So then again, the problem here is we've got this y, but we've got a dx. So we need to plug this in. So we'll go integral from a to 0 of x squared k x cubed dx. Okay, so again, at this point, we're just now we're just doing calculus, right? So this will not be terribly interesting. I'm going to pull the k outside because it's a constant. I don't feel like dealing with it. So we'll get k out front. That leaves you x to the 5th. We'll make it x to the 6th, 1/6 of that from a to 0, like that. And then, oh, sorry, that looks like a 9. And then we'll get iy equals, what's that? 1/6 a to the 6th, or k over 6 a to the 6th. Okay, questions? Okay, once you get to this point, it's mechanical, right? It's like, oh, I'm just gonna like, you know, go through these steps and, you know, whatnot. So, yeah. So, I mean, and obviously I'm not minimizing this to say like, you can't make errors, but as far as I'm concerned, like if I'm grading this, really, this is a step that I'm looking for. Like if I say just set it up, which I might do, you know, then what I'm going to be grading for is I'm going to go, okay, let's see. Like it'll say solve this by direct integration. You can get on the internet and you could type this in, and it'll probably give you the moment of inertia for that shape around this axis if you wanted. Okay, but I'm going to want to see a little more than that. So if I say like do it by direct integration, this is the step I want to see. Okay, now you could do it with your boxes the other way if you wanted to, and I'll accept that. But this is the, you know. Anyway, so let's do this particular problem didn't ask for this, but let's go ahead and get ix equals question mark. This is going to be a little bit harder than the iy. I'm going to erase some of this stuff because this will be different. You stupid lousy. Okay, so let's get rid of all this. Oh, any questions? Sorry. Please interrupt me. So if ever any of you guys become teachers, one of the things they teach you when you learn how to become a teacher, not that most college professors have really learned how to be teachers, they've just learned how to do really good research and then figured out how to teach. Not saying that we have bad teachers. I think we have very dedicated staff at UNO, our faculty. But one of the things, this is a problem that everybody has. So is you ask people if anybody has any questions, and then you wait like a second and a half, and then you go, okay, and then you keep going. And in the meantime, the thing to remember always is that people need a little time to process their question. Anyway, if ever you guys want to talk about teaching, I would love to talk about that. It is my passion. I do love it. So I love it more than calculating centroids, if that's possible. Okay, so here we go. So we're going to talk about, I'm going to draw a green line. So we're going to go with respect to the x-axis down here. Okay, so then the first question, of course, is which way do we want our boxes to go?
Parallel to the x-axis.
Parallel to the x-axis, because we want it to be parallel to this thing. So we're going to draw it here. Okay, and already you should see part of the problem here is that this is x comma y right here. Okay, and y is right here, and x is right here. Okay, notice that neither of those like is a side of the rectangle, right? But let's go ahead and get our radius. Okay, let's see, what color are we working in? Blue. Blue is my favorite color. Okay, R, especially to do problems in. So what's the radius here? How far are all the points in that rectangle from the x-axis?
Y.
Y, exactly. Okay, Y. Sorry, it was Paul Simon's song stuck into my head. Okay, so now we've got R. Now we need to get dA. Okay, so this is a rectangle. So we've got a thickness right here. Anybody? What's the thickness?
dx.
No.
dy.
dy, right, because notice it's vertical. So this is a dy. So that's a dy. So now we have to get this bit right here. I don't know what color to use here. From here to here. Any guesses?
A minus x.
A minus X, perfect. Right? Okay, because this is X. And this is A. So that means A minus X is this distance here. Okay. Parker, you see it? Okay. Austin, I don't see your face, so you're probably like off in the kitchen making a milkshake, I hope.
No, I'm here.
Okay. You're good?
Yeah.
Okay. All right. So then we just gotta, so now we just gotta, put all this stuff together and make an integral. So we'll say I, in this case, this is I with respect to the x-axis, equals the radius squared, so that's y squared, and this dA, which is going to be a minus x dy. Okay. And because we're doing dy's, so it's like the way they always, well, I see a lot of people teach this on the internet. Maybe this works, I don't know. Is they say like, okay, we're stacking these boxes in this direction. So we're stacking them from 0 all the way to B. Okay, so 0 to B. Okay, and again, the problem we always have, so is this little x right here. We don't want x's, we need y's in this case. This equation is not really going to help us with that, so we need to rearrange it. So I'm going to divide both sides by k. So let's see here, y equals kx cubed. Let's divide by k. And then let's take the third root. So x equals the third root of y minus y divided by k. Okay, and that's just horrible, right? There's really no question about it. Ix equals the integral from b to 0 of y squared times a minus the third root. Now, one thing that I'm going to recommend here when you're taking these, when you're doing these derivatives or these integrals, is we're going with respect to dy. So let's get that y and that k separate from each other. So what I'm going to do is I'm going to use exponents here, if I can. And I'm going to do the third root of, well, let's use exponents. Sorry, exponents. Come on. So it's going to be y to the 1/3 over k to the 1/3, right? Because when I get that k to the 1/3, I can just treat that like any number. I don't have to worry. I mean, sorry. I have to keep rewriting the k to the 1/3, but I don't have to like do anything with it. So it's just annoying is all it is. But it's not mathematically hard. We're just going to keep recopying it. So we're going to go b to 0. Okay, and this looks really scary, but it's scary, but it's not so bad. Okay, because we're going to distribute this y squared and we'll get a y squared minus, so what's that? 2, so we add exponents when we multiply, right? So this becomes y to the 2 1/3. So what's 2 1/3 is 7/3. Okay, over k to the 1/3. And we've got a dy out here. Are my drawings showing up on y'all's computer? On y'all's screen?
Yeah, I can see him.
Okay, I can't see them on mine, so that's interesting.
Wait, I only see Ix equals the integral from when you put y.
Do you have ay squared minus y to the 7/3?
No.
No.
Okay, yeah. So hold on. Let's something happened when I let me make sure I'm sharing screen. No, hold on. I'm gonna stop. No, if I stop share, it's gonna lose all this. Huh. Why are you freezing, you punk? You can hear my voice anyway. Oh, dadgummit. All right. Well, I'm gonna I'm gonna stop share, and I'm just gonna try to remember where we are. Let's see why. I think I got it. Whiteboard. Okay, I think we were at Ix equals the integral from 0 to b of a, oh man, I don't remember. A y squared minus y to the 7/3 over k to the 1/3 dy. Is that right? Something like that? Look at the last step. Is that right?
Yeah, that's correct.
Okay. So then here's where we are. And so then, we just have to solve this, right? And so
I think you actually had y separate.
I had y separate.
Yeah.
What do you mean?
How I have it is a the y is separate from a in how you wrote it, but it's
Oh, it's
the same
algebraically,
thing.
it's
Yeah.
algebraically the same. Okay, yeah. So we'll go ahead and solve this. So again, this looks really ugly and scary.
How did you get y to the 7/3?
Okay, so we
It's-
had y squared, and I was distributing it into the parentheses. And so on that second term, I had a y to the 1/3 over k to the 1/3, right? I don't remember well. I think it was like this, a.
Yeah, that's how it was.
And so when we go here, remember, so like, you've got y, y to the 3rd times y to the 5th, right? And you're kind of like, well, what do we do here? Well, the way we do this is we go y times y times y, that's y to the 3rd, times y to the 5th, y times y times y times y times y. So altogether, that's y to the 8th power, right? So we add exponents, right? So, sorry, this is how I always remember the exponent rules. So, so we do the same thing here. We're going to add exponents. So I've got a 2 and I've got a 1/3. So if I add those, I get 2 and 1/3. So I end up with y to the 2 and 1/3. But I don't really want to deal with y to the 2 and 1/3. So I converted that to 7/3. Okay, so that's where it came from. Okay, so then, so here, so we go I to the x equals, now again, just remember, these are just exponent rules from algebra. So this becomes a over 3 times y to the 3rd minus, and this becomes, so we're just going to add 1 to 7/3. So there'll be y to the 10/3. Okay, I'm going to put 3/10 out front. Okay, and then we got this annoying k to the 1/3, which is just going to kind of hang around with us. Okay, and we're going to integrate that from b to 0. Okay, and then we just got to plug in. So I to the x equals some really horrible, a b cubed over 3 minus 3/10 b to the 10/3, yeah, over k to the 1/3. I think in this case, it's pretty obvious why they didn't assign this one, because the answer is really stupid looking. But it's okay, right? It's okay. It's okay. The point is, could you find it, right? Like I would hope that, now, of course, I could always make an error on the exam and give you one that comes out all ugly. There's nothing wrong with that. But we like it when they come out pretty, like if we get like 1/6 AB squared or something, we're like, all right, that's pretty and, concise. But it doesn't have to work out that way. In fact, I would assume that in the real world, when you're dealing with real shapes and real things, way more often than not, it comes out to be something ugly. Okay. Now we usually gloss over that because we have numbers that we plug in for A and B, and then we just get a decimal answer and we move on with our lives. So anyway, let's let's find another one. Any questions about this? I feel like you guys are starting to see this a little bit better. Let's see if I can find one. Well, they don't have any more integratable ones. So let me find integrate. Let me find one on the internet. Integrate moment of inertia problem. Let me get images.
Will you only just give us the ones with integration?
Well, it's either going to be integration or composite. Yeah, it's they all everybody gives you the same questions over and over and over and over again. No, they'll give you yeah, so it's either by integration or composite. Maybe we should do a composite one. Let's do a composite one, and I'll just work another integration one next time. So I had planned to kind of do all either integration or composite today, and then do all integration or composite next time. But it might be good to see both. So let's go ahead and clear all drawings here. I actually I really like the integration ones because it feels like a puzzle to me, and you're just kind of like piecing it together. Okay, so okay, let's do Let's do this one. Okay, so this one, I haven't assigned this problem to you, this set to you yet, but I need to, and I'll give you a little extension on it because I'm late posting it, so it won't be due Wednesday because that would be really rude. I don't have anything due Wednesday, right?
No.
No, I
Yeah.
don't think so.
Okay, I really screwed
Will,
up.
will it just be the Connect homework, or do we have another written homework to go with it?
I haven't figured that out. I haven't figured any of that out yet. I like to have it written because I like to see your work. And I like to be able to, give you a little, because you guys may not realize this, but statics is the first course in a lot of courses, and almost all of your professors are going to require like given required solution, and et cetera, et cetera. And so to some extent, and I don't know how typical this is, but I take statics, I treat it like it's your introduction to engineering, which clearly it is. But I also treat it like I want to get you guys working systematically. That's why I'm such a jerk about the significant figures. Is I want y'all to have a certain precision in your work. But then the given, required, and solution. At least when I was an undergrad, and I've looked at most of the other professors at UNO, and they all do it as well. It's a very common thing that professors make you do, and so it's good for you to get into that habit. Yeah. So I don't know. I don't know where I'm going with any of this, except yeah. So it's important for me to look at your work and just like, my really goal in my homework is I just want to look for given, required, free body diagram, and then solution. And this is always 1 point. This is always 1 point. You've got a heading up here. If you screw up the heading, I take a point away. Free body diagram, which almost always shows up. It doesn't on these problems, but that's always a point. And then your solution. Well, it depends on how many solutions there are. So that could be from +1 to 5. And I'm not really so worried about the solution. Connect can test whether or not you can do the solutions. But it does help me, like sometimes I can like pick through your work and find where your error is. And if I can find that, then that can be helpful. So it is important to me to have written homework. I wish I could just do it all with Connect, because certainly that's easier for me. And I think it's advantageous to you in the cases where Connect does a good job of giving you like feedback, but it doesn't always do that. So that's a real bummer about Connect. Sometimes it's like, well, can't you see, and they just give you a formula and you're like, well, if I understood the formula, I would have gotten the answer, you jerk. Sorry. I'm a little annoyed that Connect doesn't give better feedback. Anyway, so let's see this, they're going to call L from here to here. So it should be obvious right off the bat that this is not a, L is 120. So let's just erase that and call it, this is 120. This is the number my computer gives me. This is going to be 50 meters, 50 millimeters from here to here. And we've got 10 millimeters here. Anyway, so sorry, I'd like to discuss, what do you call it? Philosophies of teaching. Let's see. All right, so okay, again, let's keep in mind so what they want here is, wait, hold on. I think they want IY. Yeah, they want IY. Now I think I want to remember here that this is the y-axis, so this is the one that we're going through. Okay, in this case, I think that's the centroidal axis. So they did, well, we need a coordinate for that, don't we? That's interesting. They don't tell us where it is. Well, we have to know. Huh. That's interesting. Interesting. Okay, we're going to assume, and this is quite an assumption, but we're going to assume that this thing right here, that this point, let's see, we're going to assume that that y is 60 and 60. Okay, I want to note also that this thing is completely symmetric. I didn't do a good job drawing it, but notice that this rectangle here, 10 by 50, is the same as this rectangle here, 10 by 50. Okay, so it's completely symmetric in every way. Okay, so we're going to solve for, this is given and required. They want the moment of inertia about the y-axis, so Iy equals question mark. And then the radius of gyration. I forget what the symbol for the radius of gyration is. They call it Ky. Okay, Ky. And we'll talk about that in a second. Okay, so let's get rid of all this. Okay, sorry, I've been kind of long-winded this morning. Okay, so right off the bat, you should see that this is not like the other problems. What you can do here to get the moment of inertia is you can basically sum the moments of inertia of all the shapes. Okay, the nice thing about the moment of inertia is it's completely cumulative. Okay, so you can just kind of add it up. Okay, the hard thing here is, so what you need to do, so we're going to break this up into shapes. I'm going to call this shape 1, I'm going to call this shape 2, and I'll call this shape 3. And remember, like the Iy of anything, okay, or the I is defined as r squared dA if we integrate it, right? But we're not going to do that this time. So what we just need to do is we need to figure out Iy for a shape. So Iy for any shape, okay, is going to be like, we're just going to look up the formula in the back of the book, okay? And the formula for a rectangle, let me put a rectangle here. Y in this case for a rectangle equals 1/12 the base times the height cubed, and then plus a d squared. Now this d is the same thing really as that r. Okay, and so this little bit gets added on here because of what they call the parallel axis theorem. And so we're gonna walk through this. So I'm gonna create a chart just like I would do with the centroid. Okay, and so we're gonna do shape. Okay, we're gonna get I, and then we're gonna get area, and then we're gonna get the distance squared. Okay, and I'm gonna talk about each of these as we do it. Okay, so the shape, this is shape 1. Shape 1 and shape 2 are identical. So we're just gonna kind of do those together. So shape 1, let's get the area first, because that's actually the easiest thing. It's 10 millimeters times 50 millimeters, so it's 500 millimeters squared. 500 millimeters squared, this is the same. Okay, now the I, the formula for a rectangle right here is 1/12 base times height cubed. One of the keys here is that it says base times height cubed. You have to think about what the base is. Okay, so in this case, your base is this guy. Okay, and your height is going this way. Okay, your height is always going away from the axis you're taking the moment around. Okay, so in this case, this is going to be 1/12 the base, which would be 50 millimeters, and the height was going to be 10 millimeters cubed. Okay, so I'm actually just going to go ahead and plug that into my calculator here. So it's 50 times 1,000 divided by 12 is 4166.7, 4166.7, and that's millimeters to the fourth. Okay, now the distance here, and this is key, although it's, this is the distance. This is the distance between centroid of shape and the axis, that you're taking the moment around. Okay, so basically in this case, we're going from here to here. Okay, so this is the axis right here, and the centroid is a rectangle, so it's going to be halfway in the middle of that. Okay, so you have to figure out what that distance is. So we've got 60 here. So I'm going to subtract off this 10. So now I've got 50 here. So I've got 50 millimeters here. I've got another little 5 millimeters there. So it's 55 millimeters. 55 millimeters. And we're going to square that. 50, well, I'll plug that in my calculator right here. So let's see here. Clear 55 squared is 3025. 30, oh, come on, 30, 25 millimeters squared. Okay, and then we'll do number 3. Okay, shape 3, 1/12 base times height, 1/12. The base is this little thing right here. So that's 10 millimeters. Okay, and the height is going to be from here to here. Okay, and that is, what is that? That's 100. 100 millimeters squared. Okay, and then the area of that thing is not important because this is area times the distance squared. And you
Cubed.
what? Go ahead.
Isn't it cubed?
Oh, yes, thank you. Thank you, right. Yes, come on, you can do it. Okay, good. Millimeters cubed, thank you. These are the sorts of errors that I certainly make. I'm always impressed when I give tests and I have people who get like hundreds on it. Because I'm always like, I couldn't get 100, you know? Not because I don't know how to do it. I know how to do everything. Well, everything that I put on a test, I know how to do. But what I don't know how to do is not make an error. You know, that's just the way things go. But anyway, we'll go ahead and get the area of this thing. And it's going to be 10 millimeters times 100. So it's going to be 1,000 millimeters squared. Okay, but that doesn't really matter because this distance, the distance between the centroid right here and this axis is 0. Okay, so the distance is 0. So basically now I can do this. I can say, well, so my final answer here, and you don't really have to do it this way, but this is just kind of the way I like to do it because I think it's also the way Jeff Hansen does it, but it just kind of like separates things out for you. So basically it's a summation of all of this, okay? So, or all of this, I guess. So basically I can take, so it's going to be, so the total I for this thing is going to be 2, because we got 2 of 1 and 2. These are identical. So 2 times 4166.7 millimeters to the 4th, plus the area, which is going to be 500 millimeters squared, times the radius squared, which is 3025 millimeters squared. Okay, plus this shape, which, well, let's see here, 1/12 of 10 times 100 cubed. Let's see here, 100 cubed, right? That's 1,000,000 times 10, that's 10 million. Divided by 12 equals a really huge number, 808. Let's see here, 8. I hate, this is my least favorite part of the whole course, maybe, is keeping track of these ridiculously large numbers. Millimeters to the 4th plus AD squared, which in this case, I'll go ahead and fill it in just so you know what I'm doing, times 0. Okay, and that's how we get our answer. Okay, and this obviously goes away. Okay, so if I plug that all into my calculator, I'll put IY right here. Let me go ahead and erase all this nonsense. Let me give myself some space here. So if I plug that all into a calculator, let's see here, 500 times 3025 plus 4166.7 times 2 plus 833,333 equals. Okay, we end up with a number like 30. Oh, come on. 30. Man, that's a huge number. 386666666.4. And hopefully you're seeing now why we like to millimeters to the 4th, which hopefully you're seeing why I like to do this in with 3 sig figs. 1, 2, 3 millimeters to the 4th. Okay, and you also should be noticing right now why I hate, you know, like I get this number and I'm like, I don't know what any of this means, right? One thing I will note that I think is really interesting is that as far as the ability to resist bending around that axis, notice that this little bit right here, okay, this is a big number, right? 833,000. but as a proportion of the whole thing, it's relatively small. These shapes are much more important for resisting bending. Okay, the further away you get from that axis, the better positioned that area is to resist bending. Okay, so that's like just kind of a key point. Let me go ahead and look here and make sure that we got the right answer. Okay. Actually, yeah, we're good. Okay. And then, so for this KY, this axis of rotation, or radius of gyration, radius of gyration, I'm going to delete all this. So the nice thing about the radius of gyration is that once you get, what was the areas here? So we've got this number and we've got this number. Okay. So the total area of this thing is 2 times 500 plus 1,000. So it's 2,000 millimeters squared. So we do need that number. Yeah, so let me go ahead and erase here. Okay, so one nice thing about the radius of gyration is that once you get it, oh wait, hold on, my puppy is returning to me. Hold on. Hello, how do you do? How do you do?
How do you do?
Well, how do you do?
Yeah, sure, the leash laws is.
Oh, you were up by the. Oh, okay, but he was okay. You can come in and hang out if you like. I'm finishing up here. But that's up to you. 15 minutes. Okay. Hello, my Rocky Puff. Okay. I love you too. All right. So sorry about that. So the way to get the radius of gyration is it looks like this. There's a formula for it. KY squared equals IY over the area. Okay. And so this formula is relatively simple. So the square root of IY, which is this huge number, 3866666.4, and that's probably a rounding error there to the fourth. Okay, divided by the area, which is 2,000 millimeters squared. And so if you do KY equals, you just it's basically just plugging in the calculator. So the nice thing about this, from you guys' standpoint, because this isn't terribly hard, 43.969, 970. Okay, or that's millimeters. Okay, or KY equals 44.0 millimeters. KY equals 44.0 millimeters. Okay. All right. Any questions? Sorry, I know that got a little weird there when my puppy showed up. Sorry about that. I kind of lost my concentration. I mean, he's a good dog. Okay. So the nice thing from your standpoint here with this is if you get the wrong number here, like if you were on a test and you got the wrong number here, it's okay. Plug whatever number you get in right here, plug the area in, solve for the KY, and you'll get full credit right there. So it's not a complicated procedure to get the KY as long as you can get this formula. Okay. I don't normally mess with the KY very much. I just don't really care all that much. I'm trying to think where it comes in. I think it comes in mechanics and materials. So, but it doesn't really show up in this class. Anyway, so should we do one more before we call it quits? Or how do y'all feel? What are y'all thinking? I mean, I guess I'll do one more. Let's do one more. A common thing, by the way, with this is they won't necessarily give you the centroid. So what they'll say is instead they'll say calculate the moment of inertia around the centroidal axis. And so you would actually have to solve for where this axis is. Okay. And so let me see if maybe I can find one of those. Let me see what we can do here. Let's go here. I don't want to do that one. Okay, let's do this one. Okay, here we go. All right, so this one looks like this. Determine the moment of inertia Ix bar and Iy bar. So these are the things they want. Okay, with respect to the centroid. Okay, we may not finish this one, but that's okay. We can come back and finish it next time. Okay, so we've got this, we've got like a C bar, or what I'll call the C bar. Okay, so this is 120 going right here, 120. They love to do millimeters on these problems. I find it really obnoxious. Anytime you see millimeters, it just means we're gonna have huge numbers. I think because if you use meters, you'll get really, really tiny numbers. Still, that doesn't make it okay in my book. Okay, so this is 180 millimeters. They could just use centimeters and we'd probably get appropriate size numbers. Anyway, and then this width right here is, let's see what number they give me, 30 millimeters. 30 millimeters. Okay, so they want these with respect to the centroid. Okay, and we, due to time, we're just gonna do, let's do IY, that's the harder one. Okay, let's do IY here. Okay, so it's with respect to the centroid, but they didn't tell us where the centroid is. So that's a little bit problematic. The nice thing about this is we can kind of create a chart and we'll get at it, okay? So first thing we need to do is we need to figure out where the centroid is. Okay, so remember for the centroid, we're gonna do, so the IY bar. So that means that we're going with respect to the centroidal axis, and I just don't know where it's located. So I'm gonna start my coordinate system right here. This is gonna be 0, 0. Okay, and so we're gonna say, so the centroid, in this case, X bar equals, okay, the summation of X bar A over summation of A, so the total area. Okay, so we're just gonna create a huge chart here. Okay, and so we're gonna go area, X bar, and X bar A. Okay, and that's just gonna be the start. Okay, and here's the shapes. And I'm gonna go ahead and number these, and we have to decide where to cut this. We could, so I'm gonna cut it like this. You could obviously cut your rectangles differently, but that's just how I'm gonna do this. Okay, so this will be 1, this will be 2. Again, notice the wings are the same, and this is gonna be 3. Okay, so now let's see here. The area of 1, well, that's gonna be 30 times 120. So let's see here, 30 times 120, so that's what, 360, 3,600? 3,600 millimeters, so this is gonna be shape 1, this will be shape 2, millimeters squared. And we're gonna note that for 2, it's the same thing, 3,600 millimeters squared. Okay, so now I need X bar. So where is that, where is the radius, or where is the centroid of 1 and 2? Well, it's a rectangle, so it's gonna be right in the middle there. Okay, so it's gonna be about 60 out, 60 millimeters, 60 millimeters. By the way, our expectation should be that, we're not at 60, right there. Our centroid should be back this way from 60 a little bit because we've got all this area over here. So my expectation is that X bar is going to be about 50. I don't really know what the answer is, but that's just my expectation. Okay, so my X bar A, we're going to multiply that. So we'll say 60 times 3,600 equals 216,000 millimeters to the third, 216,000. Actually, I'm just going to put millimeters to the third up here. I don't want to have to write that. Okay, so now to get the centroid, we're going to look at our formula up here, and we're going to sum these, and we're going to sum these. Oh, sorry, I forgot the other shape, didn't I? Okay, number 3. Okay, and that one has a width of 30 and a height of, it looks like 120, so 31 times 120 is 3,600. Oh, I did a good job picking. Okay, and its X bar is going to be, so again, it's a rectangle, so it's halfway out, so it's about like right there. So it's 15 millimeters. And so I'm going to multiply 3,600 times 15. 540,000. Okay, so we're going to sum all these and we're going to sum all of those. Okay, so 3,600 times 3. 10,800 millimeters squared. And then we add all those. 216,000 times 2 plus 5,400 equals 437, 400. Okay, and so I'm going to plug those in here and just divide. So I'm going to do that one divided by 10,800. Okay, 40.5, 40.5. So my initial guess over here of somewhere around 40 was pretty good. Okay, any questions about how I got that? Okay, so now I want to do the eye for all these shapes. Okay, and so these are rectangles. And so what we're going to do is we're just going to look up in the back of the book, and for rectangle, that's 1/12 base times height cubed. Okay, and where we want to remember our height is going away from that axis. Okay, so in this case, our heights are stretching in this direction. Okay, so for this for 1 and 2, that's going to be, let's see here, 1/12. So this will be for I1 and 2. 1/12. The base in this case is 30 millimeters, and the height is 120 cubed. Okay, so if we do that, that's going to be 30 times 120 cubed equals some massive number, which we divide by 12. And we don't want that right there. So we hit equals. And we get 4.32 million. 4.320 million. And I'm going to say this is in millimeters to the fourth. Okay, 433.20,000. Okay. Now for this particular shape right here, for number 3, okay, it's going to be 1/12 of this base, which is what? That's 120 times this height, which is 30. Okay, so it's going to be 1 divided by 12 times 120 times 30 cubed. Okay, a big number, but by no means big in the grand scheme of things. 270,000, 270,000. Okay, and then we're going to do area. Oh, we already did area, so we're going to do distance. Come on, we're going to do distance squared. Okay, remember the distance is the distance between this axis and the centroid of the thing we're looking at. Okay, so, and we don't have to worry about signs here because we're going to square it. Okay, so I'm just going to put the distance and I'm going to square it like this. You know what? No, I'm not going to do that. Okay, so this first one, the distance is, okay, so we're going from 40.5 out to here, to this thing, which was at 60. Okay, because it's half of that 120. So 60 minus 40.5 is 19.5. So this is going to be 19.5 squared. 19.5 squared is 380.25. Okay, and this has units of millimeters squared. So this is 380.25. And then we need it for this one. And so this is at 40.5. And this one is going over what, 15 millimeters. Actually, it's cool. We've already figured that out, haven't we? So the difference between 15 and 40.5 is 25.5. So I'll do 25.5 squared, and we'll get 650.25. Okay. And then the last thing we want, the last row is I want AD squared. Okay. And so AD squared, so that's this row, or this row times that row. Okay, so let's go 3,600 times 380.25 equals 1 million. Oh man, 1,368,900. And then, okay, Rocky Dog, it's not time. Not time for bothering me. 368,900. And then we'll do the same for this bottom row, which is 15 times that 650, not 15, 3,600 times 650.25. And we'll get 2,340,900. Okay. And so then, so now we're ready. And so the total I in the y-axis, okay, this is relative to the centroid, is, so we're basically going to sum up all of this, and we're going to sum up all of this. Okay, so so I'm going to add all of these right here. I'm going to add up all of these right here. Okay, so 4320123 times 2 plus 270,123 equals this number, 8,910,000. Okay, millimeters to the fourth. Oh, and these are all have millimeters to the fourth as well. And then we'll just do this one, which is going to be 1,368,900 times 2 plus 2,340,900 equals. So this is 5,078,700. So we're going to add these two numbers right here, plus 8,910,123, and we get 13 million. So 13,988,700 millimeters to the fourth, some insane number. Okay, equals, let's go with 14 million. Okay, millimeters to the fourth. Again, very hard to know just by looking at that number whether it makes sense. Okay, I certainly do not know this answer. Okay.
Would you ever want an answer in scientific notation?
You could do that. Yeah, I think probably in this case that might be a better way to do it. 14.0 times 10 to the sixth millimeters to the fourth would be pretty good. Yeah, I think that would be a better way to do it. I kept trying to think of ways to convert this to centimeters or something. I think scientific notation would be the way to go here. That's a good point. My answer is off of the books a little bit, so either I rounded in a funny place or something. I'm looking at their solution, 60 minus 45. I don't see what I mean, it could be that our centroid was off or something. They got a centroid of 45 millimeters. Oh, that's weird. Anyway, so there's probably an error in here somewhere. It's probably a math error. I'm gonna pore over it, but we're out of time. But yeah, scientific notation is fine. You'll see how to do this. It's basically like doing a centroid, but you just kind of add some steps. You just kind of got to keep track of what everything is. And luckily it's a composite shape, so you just got to find nice ways to cut things up. So, any other questions? We'll do more of these next time. So hopefully this isn't too confusing. It's a lot of little calculations. It can be time consuming, unfortunately. Okay, well, if there's no questions, then I will see you guys later. And have a good day. Enjoy the beautiful weather. Hopefully you guys aren't stuck studying all day. At least go outside and study. So anyway, have a good day, and I will see you guys next time.
Yeah, see you.
All right, see you, Austin. Oh, everybody's gone. Okay, let me
I just got coffee.
oh, cool. Let me stop recording.